Hello, students. Welcome to the COP 3530 data structures class. I welcome you to the class. This is an online course and we will be learning a lot of stuff during this class. I hope you guys have gone through the syllabus. I shall post a small introductory video explaining all the rules and policies about the course. Well, this course is a fundamental course for computer science graduates. This course provides a strong foundation to rest of your computer science courses, right? So you will be learning a lot about data structures like arrays, linked list, stacks, queues, trees, graphs, and all of those data structures are in the coming classes. But today we are going to start our first lecture with the term which is called algorithms. Right, algorithms are very much important. Whenever we are going to discuss about data structures, we must discuss about the algorithms, right? So we shall discuss about what an algorithm is and what is the relationship of algorithm with the data structure, right? All right. So with this, let's see what actually an algorithm is. So you can think about it. You can ask yourself. We already have been working with algorithms in our programming 1 and programming 2 classes. So basically, an algorithm is a set of instructions, a set of sequences, steps to solve a particular problem. Let me just, if I wish to write it, then I will come to the original definition. If I say, for example, steps to solve a problem, right, which is called an algorithm. Right, that's exactly what we have been doing in our programming classes. But now here are some important questions. What are those steps? Those steps should be the clear steps, unambiguous instructions. Let me give you one example. So suppose if I ask you, hey, boil an egg for me, right? That is one thing, that one task that you have to perform. Can you write an algorithm for that? Of course you can do. You can list down the steps to boil an egg. Like for example, you can say, hey, take a pot, fill in the water, turn on the stove, put the pot on the stove, then put the egg in this pot, and then keep on doing that. There are more steps, and at the end you are doing some process. The important thing is you are doing some process to get an output. So you are providing an input, you are going to process that, doing some process, and you are going to get some output, right? But this process is called an algorithm at this point, right? But now this process must be clear-cut instructions. Like for example, I can ask you, hey, okay, if I take a pot to boil an egg, what should be the volume of the pot? How big it should be? Should I have a very big pot to boil one egg or a very small pot? So it's not clear. And the same thing is, how much water should I have in the pot? Same thing, what should be the temperature of the stove while I'm going to boil it? So there are many things which are unclear. So it is easy for us to understand being a human, but when we are talking about the computers, we are writing the algorithms to solve problems with the help of the computers. All those instructions, all those steps must be clear. That is why we are saying that an algorithm is a sequence of unambiguous instructions, right? So these instructions must be unambiguous instructions. And why do we need those instructions? For sure, to solve the problem, for solving a problem, right? And those instructions, of course, we are going to write to obtain a required output for any legitimate input, which is also very important. Like, for example, you are doing the whole process to boil an egg. So you are not going to give a whole chicken to boil an egg, of course, right? So your input would be the egg actually with the water, right? So like, for example, you are writing an algorithm to add two integer values. So you are expecting the integer values, not the string values. So legitimate input is very much important. The input must be legitimate to this algorithm or to this process. One of the most important thing here is this must also be finished in a finite amount of time. I mean, no one is going to wait for the infinite amount of time. So if you are going to write an algorithm, we should be careful that our algorithm, our program is going to end in a finite amount of time. For example, if you are going to calculate the percentage of some student, the grades of the students, so that program, that software must end in a finite amount of time. So once again, what is an algorithm? Let me just once again reiterate it, because this is very important. An algorithm is a sequence of unambiguous instruction to solve a problem for obtaining a required output for any legitimate input within a finite amount of time. So this is called an algorithm. This is the precise definition of the algorithm. Now, what happens if the computer is not there? Like, for example, if you are going to write an algorithm to compute the sum of 10 integers. So you have 10 numbers, 10 integer values, and you want to compute it. And the computer is not. The computer was just introduced about 60, 70 years ago, right? Before that, the human was still counting. People were adding the numbers. People were generating the greatest common divisors, least common multiples, the factorization. The calculations were going on, even though the machines were not there, even though the computers were not there. What does that mean then? The algorithm exists even before the computers, right? It existed centuries ago. I mean, from the centuries ago. So the algorithms were there, the computers were not there. The algorithms were followed, performed, were used by human beings to follow those steps to generate the output for any legitimate input. Of course, it required more time, but no matter, the problem, the algorithm still existed a long ago before the computers. But now, since we have the computer, so we have replaced this human with the computer. But in place of this computer, you may also have a human. There is no problem. So the only thing is, you are having a problem. You are having a problem. For example, you want to sort the list of integers from lowest to the greatest integers. So you have, that is a problem, how to sort. You have a problem, then you are going to write the algorithm for that, right? Sometimes people confuse that the algorithm is same as the computer program, right? As a computer program, for example, written in Java. So algorithm is different. Computer program is different. Algorithm is something generic. Algorithm is something which is not depending on any computer and any machine. It's simple step of instruction. Whereas computer program is written in a particular programming language like Java, like C, like Python. Whereas algorithm is not language dependent. It is simple instructions, right? So when we have a problem, we write an algorithm, then we convert that algorithm into the computer program. We give the algorithm to the programmer who write a computer program for that. If the computer is not there, the human itself will evaluate it, will follow the algorithm for the input and will generate the output for that. That's how this whole algorithmic theory is working. All right. I hope the concept is now clear, that what is an algorithm and how algorithms are important and why do we need the algorithm. We need the algorithm so that we can write a blueprint, we can write the general instructions that may be programmed for computer, that may be followed by human to generate the output based on the given input, and of course within the finite amount of time. All right. Now, continuing from here, for a given problem, let's say, for example, there may be some problem. Let's say we have a problem for which we want to write an algorithm. Let me take the example, say, for example, because we know the sorting algorithm from our programming classes. So for example, the problem is I want to sort the integers, list of integers, list of numbers. I want to sort the list of numbers. Now, the thing is, if this is a problem, in how many ways I can sort a list? So the answer is, there is not only one way, there are many other ways. For example, there are more than 200 sorting algorithms available, right? I mean, in the theory. So that means for a problem, we have multiple solutions. So what do I mean is, I may have an algorithm one. For example, I have insertion sort. I have bubble sort, let me call it algorithm 2. I have selection sort, which is algorithm 3. I have, for example, merge sort, which is algorithm 4, and so on up to n algorithm. So what does that mean is, for a given problem, there are multiple algorithms available, right? Now, if for one problem, multiple solutions are available, multiple algorithms are available, how should I choose which algorithm is appropriate for me? Which algorithm should I choose? This we decide based on some theory, which is called the complexity of the algorithm. We decided based on the complexity, right? So every algorithm has a complexity. When I say complexity, complexity means two things. One is called the time complexity, right? Time complexity. Another one is called space complexity. So selection of an algorithm for a given problem depends on these two factors mainly. There are many other factors, but these two factors mainly. What do we mean by the time complexity? Time complexity is how much time is required to solve that problem. How much time the algorithm require to solve this problem, right? And the space refers to the how much space does the algorithm require to solve the problem. Space is required, right? So based on, there are algorithms for, some algorithms can can generate the output very fast. Some are slow. Some can take more space in the memory, some can take less space. So based on these two parameters, we decide which algorithm should we follow. Now, in the coming few minutes, we will understand it in more detail, that what do we mean by this complexity, and then we shall see how to compute the complexity of an algorithm. So I have taken a very simple example here. Let's say, for example, I want to calculate, I want to write an algorithm to calculate sum of the first n integers, or first n numbers. For example, first n numbers, for first 10 numbers, first 5 numbers, first 7 numbers, whatever is the number. So in how many ways I can write it? There are many ways you can write this algorithm. For example, I have written some algorithms here so that we can take the example to understand it. For example, my first algorithm, which I'm referring as algorithm A, I have a method which is a sum, which takes n as an input, for example 5. So that means I'm going to add 1 plus 2 plus 3 plus 4 plus 5. If it is 10, then I have to go to 10. If it is 100, I will keep on adding first 100 numbers. So for this, I'm going to have one variable, which is sum, which will actually hold the sum of the numbers, and then I'm going to run a loop starting from 0 to n. For example, if it is 5, I have to run this loop for 5 times, and then inside this loop, I am going to run another loop j, which starts from I. So, right, and then it also goes to the n, whatever is the number, and I'm going to add 1 into it, 1 to the sum. So every iteration is going to add 1 to the sum. And then once the both loops are over, I'm going to returning the sum. At the end of these two loops, sum will contain the sum of first n numbers, whatever n we have provided here, right? Okay, now this is one solution. Do we have more solutions? Yes, we do have another solution, could be this one, which is algorithm B. Now, in this algorithm, what I have done is I have the same sum algorithm, some method which takes the n as an input. We have the sum variable which will hold the sum of the numbers, and I have one loop which is starting from 0 to n, similar to the previous algorithm. But instead of having another loop and adding 1 to the sum, what I am going to do is I'm going to add ith value. If I is 0, I is 1, 2, 3, 4, whatever is the value of the I, I'm going to add it to the sum. And that actually does the same job. You can write this code into Java to verify that. And then at the end, I'm going to return sum. So the same job which I was doing with 2 loops, now I have done it with 1 loop, right? Okay. Now, how does this loop contributes to the complexity of this algorithm? That's the important thing that we need to understand now. So for example, what happens here is the first loop, okay, let's see. This instruction is going to execute how many times? Right? For example, this variable is going to be created 1 time. So this instruction is going to execute 1 time only. right? And I'm going to assume that, for example, 1 unit of time is required to solve, to create this variable and to assign 0 to this variable. I will elaborate this in detail in just few minutes. And then I am going to run this loop. This loop is being executed. How many times this loop is executed? This loop is being executed n times, starting from 0 to n. So this loop is going to execute n time. If the number is 5, it is going to execute 5 times. If the number is 15, this loop will execute 15 times. And now, what we are doing here in this loop, we are actually doing two things. We are basically performing three things. First of all, we are assigning 0 to I, which is just one time only. When the loop will start, this 0 will be assigned. After that, in every iteration, we are adding 1 to the I, we are incrementing I, and we are comparing it. So basically, two things we are repeating with every iteration of the loop. So that means this whole thing is being done 2 times. So I'm going to say this is going to be done 2n times. Or in other way, what I can do is I can say this is being performed 2 times, right? These two operations are performed n times. Okay. And now coming to the next loop. The next loop is again going to start from I to the n. That means if I is 0, it is going to start from 0, right? The next time I is 1, it will start from 1. The next time I is 2, it will start from 2. But it is surely going to end at up to n. And the same thing we are going to do. This is going to be executed n time. And how many operations we are performing here? The 2 operations we are performing here, right? So again, this loop is going to run n time. And now this sum equation, sum will be this. Again, we are performing 2 operations. One is the addition, another one is the assignment. These 2 operations, how many times we are performing this? This is being performed with respect of this loop, the iteration of the inner loop. So again, this is going to be performed 2 times, and n time. 2 operations are performed for n times. And once these both loops are over, we are simply returning it, which is simply one instruction for one time, right? That's what we have done here. Now, if I compute this, how much total time is taken by this algorithm to compute a sum for first n numbers, we can say that we usually refer it with a mathematical function. I can say, hey, okay, T of n is a function of time taken to compute the sum of first n numbers, which is basically what? 1, I'm just going to add them. 1 plus 1 is this one, right? This one is being taken, right? This one. And then I am going to run this. What does this mean is plus 2n. Why 2n? Because 2 operations are being performed n times. So 2n. And in this loop, for every iteration of this loop, all this complete iteration of this loop is performing. What does this mean is this loop is again going to run for 2n times, because 2 operations are performed for n time, and plus 2n time. Why? Because 2 operations are performed for n times. So 2 things are being happening inside the outer loop. That's why I'm going to have 2n plus 2n here, and plus 1 this one, the last return statement. So now if I simplify, this is going to be T of n is going to be 2n into 2n, which is going to be 4n square plus 4n square plus 2, right? Which is going to be now, hold on, we did something. Okay, so this here is the 2 only. Why? Because let me just clarify. This here is 2 only. Why? Because this n is being run. This n time is outer loop, with the outer loop, and this is being executed n time with 2. But now when we write here, we will not write 2n. We will simply write 2. Why? The reason is because this n is already with this respect to the outer loop. And now this is going to be 4n square plus 2n plus 2. That's the equation that we are going to compute at the end of this one, right? Now let's observe this algorithm B. What's happening here? The same thing is happening for we are performing this operation for 1 time. This loop is going to run again n time, and we are performing 2 operations for every iteration, so making it 2n. Again, this is going to be executed with respect to the outer loop, which is for the n time. So how many operations we are performing? 2 operations only. And at the end of this loop, we are just going to return, which is 1 time only. Now if I compute this equation now, T of n time is required for this whole algorithm, for this whole method. And then there we are performing one operation for this, right? For one time. And then we are repeating it for 2n time, this loop, which is 2n. And for every iteration of this loop, we are performing two operations. We are performing two operations, right? Plus, after this loop is over, we are performing one task, one operation, which is one times only. So if I summarize this, simplify this, which is going to be 2 into 2, which is 4n plus 2, right? That's the whole summary. So we find out that how these two algorithms are behaving with respect to the time. We have computed their time function, that if we have two loops, nested loop, it's going to be the 4n square plus 2n plus 2. I mean, this is for this algorithm. It could be different for different algorithms. And this algorithm, second algorithm B, is going to have the equation, which is 4n plus 2. Now, do we have another solution? Yes, we have one more solution here, which I am going to call algorithm C, which is for the same problem, to add the first n number. And what I am performing here is I'm using a mathematical formula, simple, right? And I am not going to run any loop. So how many operations I am performing here? So I'm performing one multiplication, one addition, one division. So three operations are being performed here. And then I'm going to simply return them, right? I'm going to simply return them. And no repetition is involved. So if I try to compute the sum, the formula for this one, the equation for this one, which is only 3, right? So nothing is involved here. Now, how this is going to give me some useful insights. Now let's understand this one. Assume that I want to add first 10 number. Okay, let's say I'm going to add first one number. So one number only, where n is equal to 1. So in that case, this is going to give me T of n is going to give me 4 into 1 square plus 2 into 1 plus 2, which is going to be 4 plus 2 plus 2, which is 8. So 8 unit of time is required to add only one number. How about algorithm B? Let's put this value here. T of 1 is going to be 4 into 1 plus 2, which is going to be 6. So in order to add first number, if the number is only 1, we need 6 unit of time. So what happens here? We require T of 1. It is constant, which is 3 always. Now, what happens if I have two numbers? N is equal to 2. So if n is equal to 2, I can just substitute 2 here for in placement of n, which is going to be 4 into 2 square, which is 4, plus 2 into 2 plus 2, which is going to give me 16 plus 4, 20, which is 22. And this is going to give me, this algorithm B will give me the time taken by the algorithm B would be 4 into 2 plus 2, which is going to be 8 plus 2, which is equal to 10. And how much time this algorithm required is T of 2 is basically 3, because it doesn't require any n, it's constant. Now, if we increase the number of the value of the n, for example, now if I'm saying n is equal to 3, so it's going to be T of 3, which is going to be 4 times 3 square, which is going to be 9, plus 2 times 3 plus 2, which is going to be 36 plus 6, 42 and 44, right? And what happens for the algorithm B is T of 3 is going to be 4 times 3 plus 2, which is going to be 12 plus 2, which is 14, right? So here it's still same. T of 3 is going to be same, 3, right? Because there is no n for which we can substitute the value. Now, if we keep on doing this, for example, T of 5, right? For one last. So it's going to be 4 into 25, 5 square, 25 plus 2 into 5 plus 2. So it's going to be 100 plus 10 plus 212. So it's going to be 112, right? 112 unit of time is required to compute the first 5 numbers. And now what happens here? T of 5 is going to be 4 into 5 plus 2, which is going to be 22. And what happens here in the algorithm 3, this is going to be still same, which is 3. What does this mean? As the number of input, as we are going to have the input size increases, the time taken by the algorithm increases. As the number of input increases, as the size of the input increases, time is increasing. Whereas in this algorithm, as soon as, no matter whatever is the number of input, even if the input is growing, the algorithm is taking a constant amount of time. What does this mean? This means whenever we have a function which computes the execution time of an algorithm, that grows as the number of element grows. As the number of input grows, the time taken by the algorithm grows. That is actually referred to the complexity, time complexity of the algorithm. So time complexity is how my algorithm behaves, how an algorithm behaves or grows when input grows, right? So this is the important study. Based on that, we will decide which algorithm is accurate. So now, right now, for these three algorithms, we can simply say that yes, this algorithm is better because it never grows. No matter whatever is the input size, it does not grow. This is the second important, I mean, this is the second best algorithm. Why? Because it grows, but it grows with its growth is not rapid growth. It grows with some magnitude, with some margin. But this algorithm is not really good because it grows exponentially. So if I try to plot it as a graph, we can actually plot the graph like this one. So what we do is we can actually write it like this one. Say, for example, we can draw it with the help of some function that we are going to do now. So on the y-axis, we say that how much time is taken. Like for the y-axis, we can say this is time, right? And for the x-axis, we can say this is number of input, right? So what happens is, at some time, my algorithm A was behaving like this one, right? In the exponential growth. This is my algorithm A. And my algorithm B was behaving like this one, which is the linear growth. Whereas my algorithm C was a constant. So we plot our algorithms as a graph, and we then observe that the growth of the function, growth of the time taken to compute, to perform a task by the algorithm, when the input size is growing, when the input size is increasing, how much time it is taken, then we decide which algorithm is better for that. In order to do so, we have a way to compute this, which is called the asymptotic analysis of the algorithm. That's what we are going to discuss now. So let me just elaborate it over here. Let's just move around with this, let's say here. So for that, we have some symbols, which is called asymptotic symbols or asymptotic analysis of the algorithm. So, okay, so asymptotic analysis, right, which we also referred as asymptotic symbols, right? There are three asymptotic symbols which are called, the first one is called big O notation, big O, right? And we represent it with the help of the big O, right? Why do we call it big O? Definitely we are going to study it right now. Big O is basically if we have a function like this one. Let me just draw it over here. Oops, I have to be okay. So for example, if you have a function like this one, right? And say, for example, we have this is the growth of my function, right? This is the growth of my function. Let me call it T of n, time taken to by my algorithm in this function, right? And if I can find out some other function which can bound these functions in a way, like for example, this one, let me call it f of n, right? So what do I mean is, big O actually refers to the maximum time taken by an algorithm to compute, to solve it. So what does this mean is, if I have a function T of n, which is the growth of my function, and I can say that no matter whatever the size of the input, it never go beyond this f of n. So this is the upper bound. F of n is the upper bound for T of n. So we call it the upper bound. Upper bound. Upper bound means this is the maximum growth of the function. My function can grow no more than f of n. So if we can find out, if we can represent it like this one, we call it the growth, the big O. This is called the big O notation, or we call it the upper bound. This is also called the worst case of the algorithm. So the worst case means that what could be the maximum in a worst case, how much time this algorithm will take. Like, for example, if you are going to sort the list of numbers using any sorting algorithm, and the list is already in the reverse order, then what would be the maximum time taken by my algorithm? I can say that my algorithm will take this time, but will never exceed this time, which is defined by this f of n. Right? That's what I'm going to say. I'm going to bound my method, bound my function with f of n, with respect to the f of n, that my function can grow no more than f of n. Right? So we call it like this one. And this one is not always true. I mean, you can see here after the sum. I mean, you remember this is input, right? This is the x-axis represent the input. The y-axis is time, right? Y-axis is representing time. So after some input, I mean, this input, let me call n naught. So we do not consider this region. I mean, in this region, what does that mean is we are not considering the small inputs. For small inputs, it's okay. I mean, it's not a problem. But the problem is when it comes to the larger input, like, for example, sorting the list of the social security numbers, which is in the billions, which is right in the millions. So then the problem, we have to see the behavior of the algorithm for the large input. So we do not want to see. That is the meaning of the asymptotic analysis. Asymptotic analysis means we want to analyze the algorithm, for very large input, right? And usually which approaches to the infinity, right? Which approaches to the infinity. For large amount of input, we are going to analyze. That's why we call it the asymptotic analysis. So, and the big O notation gives us the upper bound, no matter how big or how large is the input size. This method, this function cannot go beyond this time, beyond this function, right? So if that is the case, we write it big O of it, and we can represent it like this one. We can say that, hey, T of n, my function T of n is basically O of f of n, where f of n is another function, is bounded by f of n, right? For some region after n naught, right? For some region after n naught, and with some constant c, right? With this f of n could be some constants as well. We shall see the concept of the constants in coming video, and with respect to some with some more examples as well. And we can say that, hey, after some input n naught, right? This input n should be greater than or equal to this n naught. I mean, I'm going to now talk about this region, right? I'm going to ignore this region. We do not need this region. So for the input, which is the after the n naught, this function could be like with this one, right? And we can say that such that this T of n will always be smaller or equal to f of n multiplied with some constant. Even if you ignore the constant, it's all fine at this point. What do I try to say is this T of n will always be smaller or equal to this f of n, will never grow beyond the f of n. If that is the case, we call it that T of n is basically big O of f of n, right? Now let's move forward, and the second symbol that I want to discuss is the big omega. Big omega, second asymptotic symbol, right? Big omega, and we represent it like this one. Big omega. Big omega is the opposite side. Opposite side means it is actually the lower bound of a function. What do I mean by this? Say I'm going to redraw this once again so that we can discuss and understand it. Let's say, for example, this is the function. This is input on x-axis. This is time on y-axis, and this is the growth of my function, right? This is the growth of my function. And if I can find out another function, this is p of n, which is my function. If I can find out another function f of n, and I can bound my function in the lower way, that I can say, hey, no matter whatever input is, my algorithm will need this much minimum time to compute it. So you can say lower bound or the minimum time taken by my algorithm. Minimum time taken by my algorithm is we represent it with respect of the big omega, right? This is called the lower bound, or you can say this is basically the best case of an algorithm. What does this mean is, this is the best. If you have given me the best of best input, the small, whatever it is, for example, if you want to sort the list of integers and it is already sorted, right? So even then my algorithm will take this much amount of time. What is that amount? If I can find out with respect with, for example, in this case, I can say this is with the f of n. I will say that this is big of omega of f of n. So what do I mean is, I can say T of n is basically omega of f of n if what I can do is I can find out, of course I'm going to see it after some time, n naught. If n naught is great, I mean n, whatever my n is greater than or equal to this n naught, after n naught, if this is the scenario, what is the scenario? My T of n is greater, always greater than or equal to g of n with some constant c. So if this is the scenario, I will call it the best case of the algorithm, and we call it we represent it with the help of the big omega. All right. Whereas this one was the upper bound, right? Upper bound, big omega, big O is upper bound, big omega is the lower bound. Big O is the worst case, big omega is the best case. Okay, next, the third one and the last one, which is called the big theta. Big theta, right? Big theta. So we represented with the big theta. Big theta is like this one, right? And what does this mean is, let me just draw the graph and we can understand it from the graph. Let's say we are going to have this graph, and I'm going to say this is my input on the x-axis, the y-axis represent the time taken by the algorithm. If this is my algorithm, the growth of my algorithm, which is T of n, right? T of n is the growth of my algorithm. Then if I can find both the upper limit and the lower limit for my algorithm, we call it the theta. Let's say, for example, there is one function, say, for example, this is the function. So let me call the f of n, right? This is f of n, and then this is another function. I mean, this is the same function, for example, with this constant c1, this is constant c2, f of n, right? So what does this mean is, after some input and not, my function is bounded between the two limits, upper limit and the lower limit. So what does this mean? No matter whatever the input is, my function will have the maximum time, which is c1 fn, the minimum time, which is c2 fn. If that is the case, I will say this is the average case of my average case or average time taken for this algorithm to compute this or to solve this problem, right? This is also referred as the average case, or we can call it the tight bound, right? Tight bound mean this my function is tightly bound by the upper limit and the lower limit, right? This is also called the tight bound. And we say that, hey, T of n, my function T of n basically is theta of n, theta of fn, if and only if my function T of n is always greater than or equal to c2 fn, and my function T of n is always smaller than or equal to c1 of f of n. So in that case, this is the tight bound between these two boundaries, and we call it the big theta. Most of the time in the algorithmic studies, we will be talking about this big O of n, because we are concerned about the worst case. right? Whenever we are going to test an algorithm, we always test it for the large amount of the input. And when we test it about the large amount of input, we will always be interested to know what is the maximum time an algorithm can take, no matter whatever is the size of the input. In that case, we will go for the big O, or the worst case analysis of an algorithm. And sometimes we also go to the average case analysis of this some of the algorithms, where we can find out, we shall say, we will take the average time taken by the algorithm. Like, for example, the sequential search or the linear search. In a linear search, you may have find out the element at the index number 1, which is the best case. This is the minimum number of comparisons the linear search has to take, that it has to at least check the first index of the array so that it can find out the number is there. That is the best case of the algorithm. And if the number is find out in a linear search, if the number is present in the last index, which is the worst case of the algorithm, which means you have to scan the whole list, whole n number of elements, which is the last. You do not need to scan beyond the n, which is the worst case of the algorithm. And then in the number may also present between the index number 1 and the nth index. It may be on the index number 5, maybe on the index number 15, or in anywhere between, which is called the average case of the linear search, that we represent with theta. So if the number is present at the last index, that is the maximum time, which we represent with the big O. If the number is present at the index number 1, which is the minimum time, that we will represent with the help of the big omega, right? So that's how these asymptotic notations play an important role to analyze the complexity, time taken by an algorithm to solve a particular problem. All right. So here in this video, what we have seen now is what an algorithm is, how to specify an algorithm, how to choose an appropriate solution for a given problem when there are multiple solutions available. We have seen with one example. What we will do is we will obviously going to deduce the function. The method that we have followed here is somehow we are not going to follow in future videos. Why? The reason is this is a very simple program. So what we did is, in a simple program, we just count the number of every operations. We count the number of every operation, right? Which is not possible if the line of code are 100, more than 100 or 1,000 line of code. That involves multiple loops. It's not a proper way to analyze an algorithm to count each and every operation. So what should we do? We will obviously going to end up with finding a function with respect to the time, but in a different way. That we will see in the coming video, right? But before going to the next video, I will also elaborate one more thing here, that what should happen. Like, for example, let me take the same example. If I have this algorithm A, if I have given you this algorithm A and I say, hey, look, this algorithm is best, go and write a code for this, then probably there is another issue. Like, so for example, if I have given this algorithm to some student 20 years ago, then the computers were not powerful at that time. The computers are much more powerful today than the 20 years ago. Then the student can claim that, sir, you have seen that this algorithm will take this much amount of time if you code it, and the algorithm I have coded an older computer is taking more time, and the algorithm, if you write a code and execute it on the modern computer, will less amount of time. What does this mean? Is my claim wrong or incorrect? No, that's not the case. The problem here is whenever we are going to analyze the algorithm, this is another important point. Whenever you are going to compute the running time of an algorithm, right? Whenever we are going to compute the running time of the algorithm, which can depend on many things. Like, for example, it can depend on for example, the architecture of the processor. For example, if you have a single processor or a multi-processor, it can give you the different result, right? You can find a different result on a single processor or on a multi-processor. We have taken a very simple algorithm. Assume that you are going to test the DNA. So DNA testing is also an algorithm, right, for which you have written the program. that obviously going to be run faster on the multiprocessor computer with respect to, instead of the single processor. It also depends on the disk or the memory, the speed of the memory. What is the speed of reading and writing to the memory. It also may depend on many other factors. For example, if you have a 64-bit processor architecture or a 128-bit processor architecture, right? So it also depends on that. It also depends on the input size. As I said, it may also depend on the flow of the data within the processor and the memory, which is termed as the bandwidth. It may also depend on the bandwidth, right? So there are many factors actually for which the running time of an algorithm depends. We will not consider any of these except this input size. Why? Because we want to give a generalized description and the analysis of the algorithm. So we will only consider the input size. We will not consider rest of the things. That things are actually dependent on the machine, not on the algorithm. For example, single processor, multiprocessor has nothing to do with the algorithm. Algorithm behaves when the input size changes, right? That's one important thing that we want to notice. And now, if this is the case, then what I have to do in future, I have to actually analyze the algorithms that we will be doing throughout the course. What I'm going to do, we are going to model a hypothetical machine, which I'm going to call RAM. RAM means random access machine, some machine which is a hypothetical machine. This is my hypothesis, hypothetical machine. Hypothetical machine for which I will be using for analyzing my algorithm. And I will be assuming that for every operation, right? For every operation, this machine, RAM, that I will be using throughout the course now onwards, RAM requires 1 unit of time. 1 unit of time. Right? Which is the general statement. Now, when I say every operation, this includes every arithmetic operation, every comparison operation, right? And when I say the unit of time, 1 unit of time, meaning I will be considering it 1, and whatever the unit the machine is taking. For example, nowadays we are taking nanoseconds or the picoseconds. In 20 years ago, probably we are taking milliseconds. Before that, we were taking seconds, or even before that, we may take the minutes. Whatever it is, we are going to consider only 1 unit of time. Now, this unit can be replaced with the modern machine, whatever we are going to take. All right. So with this, I'm going to end this video. And in the next video, we shall see with some examples that how to analyze the algorithms, right? So we shall see you in the next video shortly.